All right, so a little bit of history about my team. So my team has been 3 years old since its foundations. And over the course, we have been thinking about machine learning problems exactly the same way as common just software engineering problems. So as you may know, machine learning is a science that requires the practitioners to iteratively build machine learning models, think about the process, gather some feedback, and get to the result. So over the course, we keep thinking about shortening the iterations, getting feedback of the whole process as soon as possible, because the faster the iteration can go, the more experiments we can do, the more hypotheses we can test, and hence the better result we can get. If you look at the right graph, you will see the bigger circle is this high-level iteration of solving machine learning problems. First, we got some business requirements, and then we got the definition of the machine learning problems, and then we quickly move to prototyping part. And then once the prototyping is done, we got to the productionized phase where we want to deploy the model with as simple as one click, and then serve the model in some platforms, either online or offline or in mobile devices, and then gather feedback to evaluate how good the model is. So we want to shorten the whole process. So toward this goal, we kept building common tools to automate the whole process and make the process easier, reduce the learning curves for data scientists, researchers, and software engineers. And we are thinking about how to make the machine learning model representation standard as standard as possible, and also how to allow people, mostly data scientists, to easily author machine learning workflows to train their models faster in a faster way, right? So this is our goal. With that, toward that end, so we come up with the transformers as the model representations. If you are familiar with Spark, transformers is the concept of Spark ML. So why we adopt transformers as a model representation? Because it's widely adopted as a industry standard for models. And machine learning workflow, there are many workflows out in the industry. For example, Facebook's machine learning learner, Google developed a Kubeflow, and we developed Michelangelo workflow because we believe we have our own use cases. And workflow is our way to flexibly, quickly execute a machine learning training process and serving process with the scalability and the reliability for our data scientists. Let me explain first some key concepts of the transformers. Transformer is a Spark ML abstraction of a machine learning stage that includes feature transformations, trained models that could transform input data frame to an output data frame. An estimator, so estimator is a learning algorithm or any kind of machine learning algorithm that can fit on data or train on data to learn something, right? And then be converted to a transformer. So pipeline, pipeline splits in two parts, a prefit pipeline. Prefit pipeline is just a sequence of algorithms. Either it's a sequence of transformers or estimators that executes in some certain orders, and then can be fitted on the training data set that will be transformed to a post-fit pipeline. So post-fit pipeline is converted from a pre-fit pipeline by fitting some data. And post-fit pipeline is solely comprised of transformers. Okay. Let me introduce some of the technical details about estimators transformers. So we adopt Spark standard interface for estimator and transformers, as well as our own interfaces. So the Spark standard interface is just estimator transformer interface, and then as well as the ML readable and ML writable. Why? Because we want the transformer of the estimators and transformers be serializable to external storage and deserializable as well. And the ML transformer interface defines two interfaces, score instances and score instance. Score instance is just a scoring function for a batch data set. We want this because we want to use the transformer in either our online prediction service or offline prediction jobs. So this is our interfaces. And with, by having the estimators and transformers support serialization, deserializations, we allow Michelangelo trained models to be used in non-Michelangelo platforms. And also we allow people to use their customized pipelines in Michelangelo serving platforms. Okay, so here, this slide explains in more detail what the transformer and estimator do. So a transformer is just an algorithm that transforms input data frame to an output data frame. So what it does is that it will just select a subset of the columns in the input data frame and map it to some new columns. And then output new data frame with new columns appended. So we'll see a wider data frame as the output data frame. And the estimator is a learning algorithm, as I explained before. It feeds on data. So you can think about any of the machine learning algorithm as estimators. It trains on data and then becomes a transformer. So this slide explains a bigger picture of what pipeline is and their life cycles. So as you can see, a pipeline is just a sequence of stages where each stage is, for the pre-fit pipeline, each stage is just either a transformer or estimators in a certain sequence of order. And then we fit the pre-fit pipeline on some training data set. This is called model trainings. So as the data frame passes through each stage, if the stage is a transformer, the transformer just transform that stage to some output data frame. If the stage is an estimator, for example, it's just learning algorithms, the estimator will just call the fit method of the estimator on the training data set, convert it to a transformer, and then pass the data frame through the transformer to the next stage. So after model training, so the pre-fit pipeline will become a post-fit pipeline, which consists of purely transformers, you can see from the graph. And then we serialize the post-fit pipeline to external storage systems. So we save it in a TerraBlock, which is Uber's in-house infrastructure for storage as our model storage system. And also we store the model artifacts in MySQL so that we have metadata about the models. We can look up models. We can look up the eval data about the models. And then we deploy the model to online predictions. Okay, so this is a graph shows how many customized transformer we have built, and we want to contribute back to the communities. So we have three categories of transformers. First category is for engineering. Second one's learning algorithms. Third category is just training. So as you can see from the graph, we have, for example, hashing trick functions, transformers, one-hot encodings, DSL, I will explain this in depth. It's called domain-specific language transformations. And also palette feature, I will explain as well in later slides. Palette features is a common feature that's available in the database contributed by our customers, allowed them to share common features. We also develop transformers, estimators, and transformers for learning algorithms. For example, linear regressions, GPT trees, either for XGBoost or Spark implementations. Deep learning models, for example, TensorFlow models. We support all these kind of estimators and transformers. The tuning ones is just for example, the probability calibrations, this special transformer that we apply as a post-training step, just to calibrate the predicted probabilities. Yeah, okay. So let me explain just two examples of the specific transformers we developed and we think are creative to the industry. So the first one is called palette feature transformer. So what is palette feature? So palette feature is just a common feature from a database contributed by all our customers. And this is the way we think that we can allow people to collaborate and share data. If you look at the palette feature schema, the syntax, right? So you will see it consists of 4 parts. The first part, there will be a palette prefix followed by entity name, feature group. So together, so the entity name and the feature group will define the database, the Hive database, the Hive table, that stores the feature. The third part feature name is just the column name in that half table you want to get the data. And join key is the key you want to join this common feature data with some customized basis feature data set. So this graph shows an example, right? So let's say we have a restaurant order half table that has an order count column as the common features. It has a unique UUID as its identifier. And then we join this UUID with the RS UUID of a basis feature dataset. And after joining, we'll see we got a much wider dataset. It contains both the basis features and also the order count feature from common feature store. So by the way, so when we design a feature, common feature store, so every record will have UUID column that has some meanings. Mostly a UUID will just refer to either driver UUID or rider UUID. Okay. And so what's under the hood, right? So how do we use the path feature transformer for online serving and offline serving? So left graph shows the online serving case. You will see that we underneath the path feature transformer, we have a path library. The library can be either for online mode or offline. For online mode, it will just talk to Cassandra as the common feature database for low latency read. The common feature can also be from the third-party surveys, so it's pretty flexible. And all these complexities are hidden behind the interfaces of the path libraries. And then, yeah, so the sole purpose of the online mode of the path library is for low latency read. And there's also an offline mode for path library. So in this mode, the path library will just talk to the Hive database for large amount of data loading. And then in the offline mode, so the path library will just load a batch of load the basis feature in batches and then join with the basis features to get a much wider training data set. And then it will be used by offline prediction jobs, right? Yeah. Okay. Next is the domain-specific language transformer. So let me explain what the domain language specific language is. So we call it DSL, and this is just a lambda function that can be specified by users to transform a column in the training data set to some canonical values. For example, if you look at the first example, right? So estimated distance, this is just some distance values, but the value could be null, could be missing, right? So you have to convert it first to numeric values. That's why you apply the NVAL, which stands for numeric val first, to convert it to numeric values. In case the value is missing, we'll just fill with some default value. In this case, I'll just show it default value is 1,000. But it can be more complex. You can fill it. You can specify, okay, oh yeah, I want to fill with some mean value in the training data set. That's also doable. The second example is more complex. You can see it's just the trip request time where we first cast it to a string value, which is called S value. And then we convert, because the timestamp is usually a UTC time, we need to convert it to a local time. And then we applied UTC to local time lambda functions. And then we apply the get hour of day functions to just cut it to hour of a day and use it as a feature values, right? So the code below shows how we use the DSL transformers to achieve this stuff, right? So first we construct the DSL estimators. We set the lambda rules. Lambda rules is just the type of lambda function like the one I showed in examples. And then we set a temporary HDFS folder or just local folder. I'll explain what this one does. And then we call .fit and fit in the input data frame. So what .fit does is to learn some statistics from the input data frame. I'll explain what it does. And then we call transform to transform data to its canonical form of output. Okay, so here's what was under the hood for a DSL transformer. Looking at the left side, it's just how the fit .fit method does. So at this stage, DSL is just an estimator. As I explained before, it can learn from data by calling .fit on data. So what it does is that it will calculate the feature statistics. For example, the mean values, square value, deviations, or whatever, and then generate a DSL transform class, which is a jar package on the fly, and then save it either to local or HDFS. You can customize that. And during the serving time, or transform, after the fitting is done, DSL estimator becomes a transformer. It can be used for serving, can be used for just data transformations. So in this stage, the data frame, the input data frame will just be transformed by DSL engine. And DSL engine will first load the DSL transform class from the local storage, and then transform the input data to output data frames. So this is how it works. Okay. So I will just move on to Michelangelo workflows. So if we think about a transformer or pipeline as a model representations that allows user to easily describe their models with under a common, unified, simple interface, then Michelangelo workflows is a way how to describe a training job, a prediction job very easily and flexibly. So for any of the machine learning problem, you can think of the whole process as a workflow. It's just a DAG. So for example, this is a single training, machine learning training workflow. We have a feature data preparation stage, which contains get feature stage and doing some feature engineering like a DSL, pilot feature joins, get the training data. And also we have a special stage called prefit pipeline loading, which allows us to load some predefined pipelines or even partially trained pipelines from model storage. And then the train model operator will consume both the training data set and also the prefit pipelines, and then call .fit on the prefit data pipeline to generate the post-fit pipelines. And then the post-fit pipelines will just be combined with the output DSL transformer, the output of a palette feature join transformer to get the final post-fit pipeline, which is stored to the model store by the save model operators. And after the training, the train model operator, we do have evaluate models operator, which generates some evaluation metrics for the models. For example, for linear regression models, for regression models, is whether it's what is this is log error, mean square error, whatever, or for classification error models is AOC numbers, etc. So this is the whole process. Yeah. Okay. Yes, that's right. It's only record level. It's row by row join. It's just you can think about it as a normal SQL join. Yeah. Okay. And so with this abstraction of machine learning workflow, so we come up with the idea of splitting the workflow into the smallest unit, the function unit called operators, right? So an operator is just an atomic unit that takes the input and do some transform and output some data. So an operator can output data to a variable, which is consumed by a downstream operator. So this is the way how upstream operators are tied to downstream operators. And also the input cardinality can be multiple. The output cardinality can be multiple. So we can use with this basic concept of operators, we can stitch them together into very complex and flexible machine learning workflows, like the one before, this one. So you can see that train model operator has two inputs, has two outputs. Yeah, okay, yeah. It's not stateful, so it's atomic, yeah. So it's functional, so it's not, there's no side effect. But we do, yeah, so we do have some checkpointing functionalities within the operators, but that's hide. So if you just, if there's some failures in executing operators, it will just keep retrying itself and then relying on the checkpoint without the callers being aware of that. So there's no side effect, right? And also, yeah, this concept, I think this is our second version of the operator. In the first version, we don't really use the variables to tie up the operators. We use channels, but we finally come to the second version just by obeying the design pattern of TensorFlow. Okay, yeah. questions? Okay. Okay, so logical workflow. Logical workflow is just a DAG of the operators stitched together with variables. And they have relationships determined by inputs and outputs. And again, this is the example for single model training workflow. So what's cool about it is we can do optimizations based on logical workflows. So basically by fusing operators into a subset of by fusing subset of operators into some physical tasks. Why do we want to do this? Because there's a trade-off, right? So in executing a complex workflow, there may be failures in the intermediate state, and we want to write checkpoints as soon as possible so that we can recover from those checkpoints. But the trade-off is that the more checkpoints we write, the higher amount of time will be consumed for will be required for running the job. So that means if we cut, in the extreme case, if we cast each operator into a single physical task, that means its output will be checkpointed, and the overall cost will be really large. If we fuse them together, so we only need to checkpoint the output of the operators at the boundary of the task, then we minimize the number of checkpoints written, right? So we lower the time for the job execution, but there's higher probability for failures. And this is the trade-off, right? And the other thing is that we want to fuse operators with that shares the common environment. For example, if a subset of operators they execute the same data centers, they can be fused together into the same task. If an operator should be executed on a different data center, we definitely want to cut the task boundary for it, just by making it in a separate task. In this example, so let's say in the data prep stage, our data lake is on DC number 1. Then we can fuse all the data transfer, the feature engineering operators into the first task. But the model training stage, the model training operator needs to run on DC2. This is a realistic situation because for our deep learning process, our data resides on a different data center than the compute data center, because deep learning requires a special GPU cluster that's only available on a special data center. That's why the training operator can be on a different data center than the data prep operators. In this case, we'll fuse the training model operator into its own task, executed on DC2 data centers. And the link between the path feature join and train model, this is the training data. So this training data is passed across data center boundaries. And we do have an implicit operator to copy data between data centers. Right, so this is the system architecture for how we magically make the workflow work as an entire system, right? This full stack system. As you can see, top layer, we have Michelangelo UIs, which is the presentation layers. That we allow users to send a request to request the predefined workflow. Predefined workflow means that we have the workflow coded for users. Those are the most commonly used machine learning workflows. And then users can just request them by one click. And we do allow users to author their own workflows in customized Python language in Jupyter Notebook. And we do have our own management service for Jupyter Notebook called Data Science Workbench. And then the customized logical workflow will just be will be sent to the next layer, which is compilation layer called WFO, to validate that the logical workflow is really valid and can be translated to a physical workflow. So what the WFO does is that it does two things. It first saves both the logical and physical workflow to workflow DB, which is MySQL. Next, it will send the physical workflow to the workflow engine, execution engine, which is Piper. Piper, by the way, is a data management orchestration tool built in-house by Uber. It's very similar to Airbnb's Airflow. So, yeah. And after getting the physical workflow definition, the Piper will just schedule the workflow to be we'll schedule the workflow to be executed through a job service, which is a reverse proxy. So the job service, based on the task type of the physical workflow, the job service either launches a Spark job on Yarn clusters or Docker job on Python clusters. So Python is our own resource management. It's very similar to Mesos, right? And the job service, so once the job is launched, we do have operator runtime framework to run those physical tasks. So an operator runtime framework can be either a Java framework for Spark type of jobs, can be a Python framework for Dockerized jobs. So for Dockerized jobs, so we do have some kind of special designs because each operator is represented as a nested Docker container running inside master Docker. That master Docker is just, you can think about it as an environment for the framework, for the runtime framework. And what the Python framework does is that it will first set up the local disk for as a shared space, workspace between all the operators. And then it will launch all the nested Dockers to run. And the job service do report the job status back to either Piper and also WFO. So the status will be used to determine, okay, if the job failed, the job service, Piper will decide whether we want to retry or not. And also the status will be populated back to the UI as the overall progress of the workflow. Okay, so I will talk about next a few examples of how we use the machine learning workflows to solve some interesting use cases. First one is the partition model. So partition model, we come up with the idea quite a long time ago, right? So it's a concept used to solve Uber specific problems. So at Uber, we typically find that the data set is not really statistically coherent. So data set may contain data from 300 plus cities. And sometimes we find that the distribution of data in San Francisco is quite different from that in Seattle. And we want to partition data by city ID so that we have a more coherent data per sub data set. That's how we come up with the idea of partition model. So the process is pretty simple. It's data driven. So we first got a global data set. And in this example, partition the data first by city ID. And then we partition the data according to cities. So in the second level, each O will represent a sub data set for that particular city. And then we further partition by region ID. Internally, we call this vehicle view ID. So we have a two-level partition hierarchies. And the idea of partition model training is pretty simple. We just train a model for each partition of data. And then in case if a child data partition doesn't have enough statistics, for example, it doesn't have enough labels for one class, we just cut down, we just prune that model and then let it fall back to its parent. This is the basic idea of partition model. So before we have the MA workflows, we only hard code this partition model workflow in some kind of a YAML file. It's pretty ugly, driven by Woozy. But now we have a more flexible workflow description language that we came up with a logical workflow like this. So what's special is that we have after data preparations, we do have a partition plan stage, which partitions the input, training, and test data set into subsets data according to the partition keys. And then we send the partition data to the training pipeline for model training. This is just logical description. So let's look at its physical counterpart, right? So there's not much difference for data preparation phase, but for model training phase, you will see it's quite different because we have multiple sub data sets, and for each data set, we want to train the model. And model training is an expensive process, so we want to parallelize the training process with multiple Spark jobs or just Dockerized jobs, and then this is why we fuse we split the model training branches into multiple slots of jobs. And then we do have a model aggregation phase called model assembly operators in a separate job that will just wait until all the parallel training branches to finish and then gather the models and then assemble them together to get the final partition model. That's the physical workflow. Okay. This is a UI example of partition model training for optic model. This is a model developed by the dispatch team for one of their applications. So if you look at the UI, you will see 6 submodels. What it means is that we have 6 partitions. Right? And then the partition key is really, if you look at the partition key, it'll be vehicle view CTID at first. Oh yeah, just vehicle view ID. Yeah. Okay. Next use case is the hyperparameter search. And let me give you some background about hyperparameter search. It's just a process where we want to automatically find the best model hyperparameters. So hyperparameter is any of the parameters about model that's not really learned from the training data. And there's 3 search strategies. The first one is called grid search. Second one, random search. Third one is a Bayesian optimization driven search. Right? Yeah. So grid search is pretty naive way of finding model parameters. It just finds all the combinations of parameter combinations and then do evaluations, train models for each of the combinations of parameters, and then evaluate the model, find the best one. So it's really time consuming because the search space increases exponentially with the dimension of number of parameters. So we came up with the random search, which is the subset, just the searches over a subset of the grid search. Bayesian optimization is an adaptive approach that will just define the next suggested hyperparameter values based on previous search results. So if you're interested in Bayesian optimization, there are lots of online resources. And again, this is our system level design about the hyperparameter search. We do have an auto-tune service, which is black box optimization service that provides the 3 search strategies. We have the HS workflow that depends on auto-tunes for parameter selections. And then we have a model metadata tagging system, which is Elasticsearch driven tagging system that allows the auto-tune to leverage some historically searched result to just to start up very quickly with the initial good estimate of the hyperparameter set. Yeah. Okay, this is the logical workflow. And physical workflow again, that in the model training phase, we parallelize the process because we have many hyperparameter combinations to try, and we want to expedite the process. This is a result of a hyperparameter search. You can see that the list from the list of child models, each child model represents one trial of the search. There will be one best model according to its AOC figure. Yeah. Okay, so last example is model manifold. I'm not sure if you're familiar about manifold concept. It's just a framework that allows people to transparently diagnose the model performance. Right, so think about this. Machine learning development is a 20-80 split, meaning that 20% of time is used to develop model and 80% is used for tuning the model performance. It's really tedious. And we want to make this process as fast as possible by providing model manifold. It allows the customers to train multiple models with different feature sets or even different model types and compare the performance and figure out why one model is better than another. So this workflow represents how we use the different models, trained models to score a common downsample dataset and generate a score dataset. And this is the physical workflow. So this is the UI of the model manifold. As you can see from the last graph, let me just go down, roughly explain this. So we do have 2 panels. The left side is the performance panel. The right-hand side is the feature attribution panel. If you look at the performance panel, you will see the x-axis is just the value of one of your chosen model evaluation metrics. In this example, it's the log loss. The y-axis is just the height of the curve is just the distribution values of the performance. And we have multi-way of plot, meaning that we compare models for 4 segments of the input training dataset. And then if you look at the top figure, you will see that the green model, which is deep learning model, tends to have a lower log loss compared with the XGBoost model, so it's better. As you go downwards, then if you look at the last figure, you will see the green one is better, right? Because, sorry, the red one is better because it has a smaller loss value. So this means the XGBoost model is better than DL. And if you look at the size of the data segment, the first line, we have 7,000 plus data points. The last line has only 100 plus data points, meaning that for the majority of time, deep learning is performing better than XGBoost. And if you want to figure out, okay, so why for some data segment, why one model is better than the other ones, you go down to this figure, which is a feature attribution view. You select those data segments of interest, and then look at the compare the feature distribution differences for the corresponding data segments. So the top three curves, you can see some difference from those. Yeah, in this case, I think we select two data segments for comparisons. The top three plots shows the difference. There's some difference. The red curve tends to have lower values than the gray curve. But for the bottom three curves, there's not much difference, meaning those features make no much difference for those two type of models. So this intuitively gives some insights about that may explain why one model performs better than the other one. So this the applications. Okay, so before I end my presentation, I will talk about our open source roadmap. So we are quite ready to open source transformers. It's pretty clean code base. For MA workflows, it's pretty complex. It's a full stack thing, so there's a longer way for us to open source. But right now we are on the track, so we will open source the operator runtime framework first, with eager and lazy mode, and then we plan to open source a few strategic machine learning workflows. And then we will materialize our Python SDK, which is the domain-specific language for workflow authoring.